Assalamualaikum warahmatullahi wabarakatuh. Good morning all. Welcome to my presentation. First of all, I would like to thank all of you for viewing my presentation. Let me introduce myself first. My name is Kustanto. I am mechanical engineering lecturer at Blitar Islamic University, Blitar. From 2017, I was a doctoral unit student in mechanical engineering at Brawijaya University, Malang. And I'm happy to be here today to present my latest finding on environmentally friendly reduction of graphene oxide. This presentation consists of 4 parts. First, I will start by talking about the introducing. Next, then I will focus on the theory of graphene material and their derivative. Next, method of developing reduce synthesis of graphene oxide, and finally, result and discussion. This presentation will take about 15 minutes. So let me start with a paper title, Extract Katuk Leaf Sauropus Androgynus for Structure Restoration Electric Graphene Oxide as a new reduction and efficient alternative. Introduction. In recent years, graphene, a two-dimensional lamella of sp2 carbon atom structure, arranged in a honeycomb lattice structure, has become a magic material due to its unique physical and chemical properties, such as unique electronic, optical, mechanical, and catalyst properties. Another derivative of graphene, graphene oxide, or GO, is an oxidized form of graphene, in which the functional groups are arbitrarily placed and collected randomly. This results in the eruption of the electrical and optical parts of graphene, so that electron transport become far away and then to be resistant to accepting electron. Reduction reaction. Reduction graphene oxide, or RGO, is a type of graphene that contains oxygen functional group, including hydroxyl group, epoxy group, carboxylic group, and has several interesting properties that are different from graphene. By reducing oxygen to graphene oxide with environmentally friendly reducing agent, such as a Katuk leaf extract, a reduced graphene oxide is obtained, which is abbreviated as RGO. Katuk leaf extract, which contain the main molecule racino and camphorol, is a natural antioxidant that is environmentally friendly. In this process, the graphene functional group is removed, but it still contains residual oxygen, heteroatom, and a structural defect that degraded its quality, having a lower quality compared to pure graphene. RGO is still an outstanding material for a wide range of applications, as it resembles coarse and unattractive manufacturing process compared to pure graphene. Especially is this preferred in applications that require a large amount of material. Experimental procedure. Graphene oxide was synthesized by the modified Homer method without using hydrogen peroxide in the synthesis sequence. In sulfuric acid 140 ml, sodium nitrate 5 plus 2 gram, and graphite powder 5 gram were mixed together. By cooling in ice bed, next potassium manganate 12 gram was added to the mixture, keeping the temperature below 20 Celsius degree, then processed by approximately 1.5 hours until the temperature show 80 degrees Celsius. The graphene oxide 0.1 mixed into the 200 ml of its extract Katuk leaf and ultrasonification process was continued at 50 watts for 2 hours to obtain homogeneous graphene oxide dispersion. After the graphene oxide was completely dispersed in the leaf extract, the resulting resolution was directly placed into the glass beaker with continuous stirring at 50 degrees Celsius for 24 hours. Then the product was washed several times with DE water and dried at 60 degrees Celsius for the hours in the oven. Result and discussion. In essence, the FDR spectrum of the leaf extract reflects the presence of various functional groups associated with antioxidant phytochemical in the form of resianol and camphorol as the continuated molecule. The FDR spectra of reduction graphene oxide show reduced intensity of peak at 2926 and 2000 ahead of 159, corresponding to the strength vibration of the hydroxyl group. Moreover, the peak was at 1780.60 and 1702.51 was suppressed after reduction, indicating the removal of most of the hydroxyl, epoxyl, and alkoxy oxygen species from graphene oxide, so that the efficiency of the reduction value is obtained by 83.3%. The absorption properties of nanoparticle can be well understood using UV visible spectroscopy. Furthermore, the UV-vis spectrum of DPP high Katuk leaf extract, the extract in shown in figure. The UV-vis spectrum of DPP high Katuk leaf extract show the absorption of oxidant, again reactive oxidant, along a broad like spectrum up to 370 to 800 nanometer. This indicated that the compound in the extract are absorbed, which is active, again reactive oxidant. Graphene oxide showed an absorption peak at 227 nanometer for graphene oxide, which was reserved to 276 nanometer for graphene oxide reduction. This shift in graphene oxide reduction is mainly due to a change in the electronic configuration of graphene oxide reduction during the graphene oxide reduction process. Moreover, the absorbance peaked at 227 nanometer originated from the aromatic rings transaction, whereas the red silver peaked at 276 nanometer originated from the bond transaction embedded in graphene oxide reduction. As shown in a table, energy HUMO has decreased from 4.45 in Ko to 5.43 electron volt in the nano Ko and RGO. And energy LUMO has increased from 2.40 to 3.46 electron volt. As a result, the nanoband gap energy are 2.5 and 1.95 electron volt respectively. The band gap energy of RGO SA 200 indicated the restoration of the electrical function of graphene. The excitation energy is inversely proportional to the mixture coefficient of the wave function. As a result, the similar HOMO-LUMO energy gap requires a lower amount of excitation energy band gap of 1.53 electron volt. The electronegativity molecule is the negative of the electronic dipole potential. The higher value of the electronic dipole potential of the RGO SA 200.45 electron volt is associated with more possibilities of swapping its electron density in the ground state. Resistance is associated with the level of crystalline nanoparticle. The higher the degree of crystalline nanoparticle, so it is resistant to accept the change in electron density. Reactivity is identified as the opposite of resistance, where the lower the degree of resistance, the more amorphous the nanoparticle. Thus, the lower the resistance value RGO SA 1.1 electron volt, then Ko 0.98 electron volt indicated a greater affinity for change in the number of electrons. Conclusion: the reduced graphene oxide sample with Katuk leaf extract have been successfully synthesized following a sample two-step approach. Next, the FDR spectrum confirmed the success of RGO sample reduction, and the oxidant reduction efficiency was 83.3%. Next, further characterization by DFT analysis, RGO SE 200 showed electrical functional recovery of graphene, proved to be more energetic than Ko. Next, RGO can further react with other organic molecules of polymer via the remaining oxygen group. which make them ideal candidates of nanofiller for high-performance RGO-based polymer nanocomposition. Okay, thank you so much for your great attention. Assalamualaikum warahmatullahi wabarakatuh.